resistant design and not earthquake proof design. If you know the demand, you can design for it. If you don't know the demand, you will not be able to design for it because that can be any number larger than what you already know. And therefore, deformability is the key if you want no collapse. This is what we will notice, that we are not talking about force levels at all. Force levels don't matter. Even at a low force level, the red one has fallen down. Even at the large force level, the blue one will fall down, of course, after a lot more shaking. So our emphasis will be on deformation in structures. We also need to talk about a concept of chain analogy. You have a chain and it is made up of links. Now, the ductile link is only one of them, which is the green one, and all others are brittle. Ductile link is 10 times more expensive than the brittle links. You can use the brittle links in large number, but you can use ductile links only in small number if you want to make it an economical structure. So the first question is, where would you place the ductile links? Second question is, how would you design the structural links? So where would you place the ductile links? We'll answer in a moment, but how to design will definitely show you immediately now. But before I move forward, I must mention here that when you impose a displacement at the end of the chain, relative displacement at the end of the chain, what you will notice is that the chain will snap when the weakest link gives up. And that is the bottom line of what we are talking about today. The ductility of the chain is the ductility of the weakest link. Now let's look at a case here. I have two examples. I have a weak brittle link on the bottom side and a strong brittle link on the top side. When I say weak and strong, it is with respect to the ductile link. And so what will be the consequence? The first one will be governed by the weak ductile link, and the second one will be governed by the brittle ductile link. And the net chain performance will be very brittle in the second case and ductile in the first case. So then the concern is, how do we design it? So first is that you have identified where the weak link will be, the ductile link will be, and you design for that. When you design at a level, you will get an overstrength thanks to partial safety factors for materials and also the partial safety factor for loads that we have used. Now, this overstrength becomes the design force for the brittle links. And since they also have partial safety factor for loads and materials, their overstrength will be higher. So very clearly, when you start pulling that chain, the only one to really give up will be the green link and not the orange or the yellow links. That is how we will get a ductile chain. Now, in buildings and structures, if you ask, what is the location of the hinges, then you'll start talking about who is more important between a slab and a beam and a column and a joint and a foundation, column and foundation and soil. You start worrying about all the 5 items that are there and then say, okay, let's agree on what is acceptable. So any relative damage which is going to have severe negative consequences, we will avoid. So between beam and column, we say beam is okay and not column because column is holding the beam. Between column and joint, we will say column is to be protected because joint is actually doing more hard work of transferring all the forces from the slab beam to the columns. And between column and foundation, we say column because foundation is really holding up the whole building. And between foundation and soil, we'll say, no, it's the foundation the soil that we will hold up everybody. So foundation is less important than the soil here. So this is the way to fix the location of the hinges now. We'll go a little more and be a little more specific. But before I go there is a misnomer in the market about what is ductility, and I want to get rid of that misnomer. So the word is flexibility, and you may be aware that when babies are born, they are born with about 300 bones. And as they start growing, the number of bones don't reduce, but they fuse into each other, some of them, and that is how the number reduces from 300 to 206 finally. Okay. So your body is nimble still, but when you reach 206 bones, you will get the Olympic medal. And after that, you have to exit because after that, your flexibility is going to reduce. Over time, your flexibility in the body is going to reduce. What is flexibility? If you want to look at yoga asana, you will say the Uttarasana is our example of how to bend backwards and how to bend forwards, both of them. But this is not ductility, and this is flexibility. And this is where, in many texts and many documents, we have read that ductility is shown as this, which is not true. Because all of these people are not going to inelastic behavior. If they go to inelastic behavior, they won't stand up again, right? So they are all under within elastic behavior only. Only thing is the dimensions are allowing them to do that, and the degrees of freedom are there because the bones are smaller in size and larger in number when you are younger. So as you get older, constraints start growing into the body. Now there are six systems in the human body, and we'll compare that with the buildings, and we will say that out of the six systems, today's discussion will only hover around structural systems and not the other systems for the moment, for the purpose of today's discussion. And I'm saying geometries are one of the biggest worries that we have, right? The larger is the geometry, the lesser will be your freedom to move around and move around without any constraints. But if you say larger is the mass, then you're going to start playing with the stiffness and strength of the structure. But what is crucial is that we know the difference between flexibility and deformability. Flexibility is all elasticity, and deformability is with inelasticity, right? We have two systems here, the green system and the blue system. So let us pause for a moment here and define what is ductility. It is the capacity to sustain cyclic deformations with damage, but without any collapse, right? So the structure is able to go back and forth with inelastic actions and is not collapsing. Now, this picture, we are only showing monotonic action here, but the blue one will tell you how much is the inelastic deformation and how much is the elastic deformation. I can show similar arrows for the green one also. But since space was small, I thought I will show it for the blue one alone. Now, what is ductility? The maximum displacement to yield displacement is at this level of a structure. We will use this definition. This is called the displacement ductility. And so the first case has less deformability, delta max. The green structure has less deformability than the second case. But the bad news is that in the second blue case, it is less ductile because its delta y is very large and delta max is only moderately more than that. So the ratio of delta max to delta y is much better in the case of the first green structure. Now you might say, why does this ratio come into picture? It controls many things, including how much is the demand from the earthquake side. Stiffer structures tend to get lesser displacement demand on them than flexible structures. And that is the reason one of the important requirements in earthquake risk design is that we should have
Afternoon, sir.
sufficient strength.
Sir, actually, a few years ago, MORTH had appointed three of us to investigate the collapse of Kota Bridge.
I request you to someone.
Sir, I'm just interrupting at this position. We have a question and answer session at the end of the program. So can we raise the question and answers at that time? So let Professor Murty continue with the lecture.
Hands up. Hands up, I pray that is okay with you. Okay, looks like we lost connection with him.
Sir, please continue, sir.
GG. So the factors that really contribute to the ductility, the controlling factors, are actually the geometry of the structure, the strength of the materials that we have, and the structural configuration that we use. Right? All of this is finally closing into that last one point of deformability. So we need to have large deformability. We also need to have large ductility. You'll ask why large ductility? Because the area between the two vertical dashed lines is the amount of energy being absorbed by the structure that is being fed by the earthquake. So inelastic energy is what we are looking at when you look at the philosophy of structures to undergo damage and resist earthquake shaking. Now let me come down to steel structures and talk about how we are assuring this deformability in steel structures. So for that, our focus now is ductility at 5 levels. So there are 5 levels of ductility that you can understand. First is, and we'll go from whole to part. First is that you need large deformability and ductility in a structure, for which you have to make sure that connections don't get into deformations, for which you have also then you have to come down and say the members should not get into undesirable actions and no geometric effects and only material effects, for which you have to make sure that the plates don't get into geometric effects and plates and sections, and because of the plates, the sections don't get into geometric effects. But finally, we are saying that to begin with, the material itself must be having very good ductility. So the summary is that we have a material which has good material nonlinearity, but then en route, we get stuck with a unfriendly neighbor called geometric nonlinearity. And as a consequence, we have finally in a structure a compromise of geometric and material nonlinearities. Now, the combined geometric and material nonlinearity is where the ingenuity of the designer comes into picture. When I say designer, a metallurgist is also part of the design, right? The market person who is selling the steel is part of the design. The code is part of the design. The classrooms are part of the design. Continuing education is part of the design, not to talk about the architects and engineers who are designing to be part of the whole process of design, right? So if you want the country to prosper, you need each state to prosper. For each state, each district for each district, each town for each town, each neighborhood for each neighborhood, each street, and for each street, each building, and in each building, each person has to be prosperous. Likewise, the material has to be prosperous to begin with. Their combined action together as a plate or a section has to be good. Their combined action over a length of the member has to be good. And then they must be connected properly. And then finally, the structure must have sufficient ductility, which can resist the earthquake shaking. So this is the 5 levels that we're going to talk about. So we need good structure ductility. And so we need to avoid all the undesirable features. What are the undesirable aspects? The geometric nonlinear effects in sections, members, and in connections. And we need to enhance material nonlinear effects. So the entire effort of all standards is actually to replicate the stress strain curve of steel in the structure. But en route, these 3 friends or 3 neighbors that we have are actually causing a little worry for us. Let us see how much we can handle. Let's go one by one out of these 5 items of ductility. Let's do material first. So today's discussion is steel, even though I'll talk about structural steel, but I'll take an advantage of the opportunity to talk about steel bars in brief only. So steel bars as a material, the newer materials are seeing very good initial yield strain, and they also have a reasonable rupture strain. So we are having a ductility at a material level of about 100. Now, the new bars that are also coming up, the TMT bars, these reasonably higher strength 550 plus bars, are also giving us a ductility of about 100, right? So if you go higher, you notice, those of us who are metallurgists will know that you have to add some carbon. And as you add carbon, this number will run down from the large number. At this point, I also want to tell you that the elongation is not required for structural engineering purposes, for the purposes of strength, but they are required for making bends and hooks. And so when you ask for 14.5%, your mandrel diameters, when you do the bends or the bars, are the ones that need to be appropriate. I'm not wanting to discuss this subject. I'll leave it at this, and you can compare what are the mandrel diameters approved in the Indian standard, current Indian standard. But definitely, they're much smaller than what is being sought here. The small mandrel diameters of 2 and 3 diameters is possible only when your steel has a strain, rupture strain of 25% or more, and only then you can have small diameters. That's why a large number of construction companies are complaining that our bars are rupturing at site, and QA, QC are having conflict there because the mandrel diameters are unduly small in materials which are not having that much of elongation, like 14.5% bars will not pass a mandrel diameter of 2.5 or 3.5 or even 4.5. It will not pass that. One of the concerns that we are seeing in the new bars is that the uniform, the TM ring that we are supposed to see, the tempered martensite ring on the perimeter, which is a hard material, which is actually enclosing a softer, the ferrite pearlite material, is actually not getting developed fully. And hence, we are seeing a rupture again when the bars are being bent. Steel sections on the other side started with tapered flange sections, and we are happy that they have now migrated or are in the process of migrating to parallel flange sections. And the classical mild steel is still giving us the beautiful 300 as material ductility, but the newer materials are actually dropping down on their ductility. The newer materials are dropping down because their yield strains are higher. And while mild steel enjoys very low yield strain, and for the large rupture strain, we will be able to get good ductility, but that's not the story in the case of high strength. The liability is epsilon y is itself your enemy. Now, there are two things that are bothering us in design process. One is that the sigma y, the yield strength ys is not ys. And second thing is the ultimate UTS is not UTS. There is an increase in those values than the characteristic values. The fact is, when you have each of them varying, the design has to, we just talked about our ductile links over strength has to become the design force for the brittle link. So if this is the ductile link, if this member is the ductile link made of this material, I need to know the top of the red as a basis for our design. And that is where the trouble is, that we are going to look at Ry times Ru as a basis. So if Ry is going by 25% and Ru is going by 30%, on the whole, there's a 60% increase. Your design will go out of control if you have just done using characteristic values. And that is where you will see in some standards, they'll ask us at least 25% more overstrength has to be considered for us to be reasonably safe. And in some cases, it is 40%. Now, remember that point. Let's come to another property called toughness, the Charpy V-notch value. All of you are familiar with this, that we need to see that depending on which weather condition we are building the steel structure in, we need to appropriately have the correct steel for it, right? If you're going into low temperature, we have to be very careful because we don't have enough toughness at low temperature. So the larger, the better for us. And so this is a serious study if you're building it in the areas where we have snow for a significantly large duration of time. Alternately, you will notice that you will not be able to hold up too many stories on that structure, or you will not be able to hold up very severe shaking on that structure if your steel is very brittle here. So we need to recognize the conditions and use the appropriate steel for that purposes. When you look at our chart in the Indian standard, you will notice that there is a minimum value given to us that we need to ensure. And for the purposes of design of our structures, we are required to use the correct steel. So if you're in cold temperatures or in fire conditions, you will have to choose the CVN value carefully. And this is one of the issues for cold temperatures is actually the toughness value. And so you will try to push the toughness as high as you can. And so we need to engineer such a steel which will handle the loads that are expected in the cold areas. And when it comes to high temperature conditions, which is especially fire induced, let us say, you need to have a decent amount of endurance in the steel structures. And that endurance will need to say that at least up to about 300 degrees centigrade, I'm not having any loss in the properties of the structure, of the material. And thereby my structure also has the assured plastic moment capacity and so on. Now for this, the next property that we are worried about is weldability, and the carbon equivalent will tell us that if you keep this as small as you can, then you will make a very good structure. Again, I have marked up the green box for those materials which are generally considered to be sufficient for, considered to be good for earthquake resistance, and which basically brings us down to Fe 250 and Fe 350 kind of number that we are traditionally used to. Now, the next point is that bolting and welding are the two contesting factors. Over the years, bolting has been losing its sheen because of the fact that the number of bolts is too many. And site bolting is also having the challenge of quality control, quality assurance. And hence, we are having to see if we can improve the efficiency at site. And hence, we are trying to go towards welding. But when you go towards welding, we realize that there is a second order problem that we are buying in, and that is called the heat affected zone. Because the materials are going to higher temperatures, and also there's a new material, the weld metal, that is coming into picture. There is a certain amount of chemical actions that are going on here because it melts and mixes with the filler material. And that is where we are having a weak spot for us in the course of our preparing the welded connection. Also, the way the members have been manufactured is important for us. If the cooling rate used is very high, then you will see that the grain size is very small, and thereby we will have trouble. It is generally said that the larger is the grain size, the better it is for us from the point of view of ductility of a material. You see this green curve, it talks about ductility of the material. And the blue curve is the tensile strength of the material. Okay. So what we notice is if you have high tensile strength, you have low ductility. And if you have high ductility, you have low tensile strength. So what it turns out is that somewhere we need to strike a moderate balance between ductility and strength. And we cannot unduly go too high on strength because we will lose our ductility. Our worry is on the left-hand side where we're trying to increase the tensile strength, and in the process, we are not getting much ductility. That is where our worry will be. And so we need to be extremely careful. How do we get careful? We need to do enough number of studies on steel as a material, steel as a section, and steel as a member, and steel in a structure. All three have to be put together for us to be able to say that, look, I'm confident that I can use this strength of steel, steel made of this strength, even though it has certain level of ductility. I assure that for those conditions that are prevalent for the design purposes, we can say, okay, let's say we will use it in earthquake zones 2 and 3. We can assure you that this is good enough for you. But in higher zones, we have to be a little modest because lives are at stake. We can't be looking just at the professional development side. Let's go to the next item, which is a section. we are familiar of the concept of buckling. In fact, when you talk about steel structures, you get chills in your spine because only one word, and that word is stability. And what is that word? The more slender you are, the less likely you're going to use the material properly. On the left-hand side is the red part where you are using material very efficiently. And on the right-hand side, which is green part, you're not using the material efficiently because geometry of the member is actually going to take away much of the magic, and you are reducing the ductility. You're not capitalizing on the ductility of steel structures. For example, we make eye sections, and you look at a web, it is held by both the flanges at the two ends. It's relatively restrained. But when you come to the flange, it is held at the middle, but not at the tips. And so there is extra freedom for that tip to run away in whichever direction. And that's what we see as flange buckling, web buckling, and flange and web buckling combined actions coming together. These need to be prevented if you really want to have plastic actions induced in the structure. Now, when you look at what are those detrimental effects that get into compression actions, it is the axial force, the nature of the axial force. Is it linear or is it a uniform action? That is what we want to see. Boundary conditions, have they been adequately restrained, the plates, or no? And then loading conditions, is it cyclic or just simply static? So the three actions that are typically imposed on steel structures made of steel sections will be axial compression, bending compression, and shear compression. Now, when you take this section and put it in as a member, you will notice that plastic actions. I'm giving you a simple example of a simply supported beam. We are expecting a plastic hinge to be formed at the center of the beam, in this case with a concentrated load. And so we understand the length of plastic hinge will be different if it is a concentrated load or a uniformly distributed load. But what is important is that we are able to reach the plastic moment capacity of the beam without any other detrimental action. If you choose the left-hand side two sections, you're more likely to reach the plastic moment capacity. But if you choose the right-hand sections, you're less likely to reach the plastic moment capacity, right? There's yet another issue that is bothering us in steel hot rolled sections is the matter of residual stresses. They can be as much as 30% of the yield values. And they're not uniform. They vary because the tips have more freedom to cool faster and the junctions are less free to move faster. So you will see that they will cool at differential rates. But what's the impact of that on moment capacity? As you can see, the more is the residual strength, the early is the yielding of the member. And yielding is very crucial for us. If you remember, we talked about ductility. And the damage will start happening early in the case of the high residual stress stories. As a consequence, the design of the compression members, you will notice that that was the case of bending that we talked about. Here we're talking about real direct axial actions. Under pure axial compression, you will notice that the combined effect of the material geometric nonlinearity with the residual stresses coming into picture is even more severe. And so while this is material nonlinearity and this is geometric nonlinearity, that's where the design stands to account for both material geometric and the residual stress effect. Now you take this into cyclic behavior. So you will need to protect the members which are under cyclic compression actions. Under this, you will notice that the B by T's and D by T's, the flange thicknesses and the web thicknesses need to be reasonably high. And experiments have shown that there are limits that we need to adopt during our manufacture to create sections that can indeed develop plastic moment capacity. Once again, why plastic moment capacity? Because material nonlinearity, we don't want any geometric nonlinearity. Look at those pictures where you have D by T's or B by T's to be very small. You will notice that you're not able to reach the good plastic moment capacity, the members are failing well before that. So the design codes will tend to now give you classification of sections based on B by T's, D by T's, also based on the member lengths here. And if you look at different standards, they'll give you different names. And not to talk about names, but the important thing is what is your application and how much action do you want? If I look at the earthquake conditions, we are looking at ductile sections and we want the section to be compact. But watch out, compact is named differently in different standards. So be very careful. Don't go by the name. Look at the slenderness ratios, and only then you will see that where you're able to get to the left extreme end of it and maximize guarantee the formation of plastic moment capacities. It is that section that we can allow in our structures. So material yielding, geometric actions, and this is what we are looking for. You can see the stress strain curve of the material on the right hand side is not touching the stress strain curve of the native steel material. In the middle case, it's come into the plateau but not risen into the strain hardening region, and here it has risen into the strain hardening region also. So the lesser is the slenderness ratio, you're going to mimic the stress strain curve of the parent material as much as possible. So strain hardening must be permitted, and you need to ensure the D by T's, B by T's such that strain hardening definitely happens. Mere plastic range is not sufficient for earthquake shaking. You need to build some strain hardening also into the structure. So the ultimate deformation capacity of a structure will depend on what is the ultimate curvature capacity of the structure. And so we need to enhance that as much as we can. Of the section that we need to enhance its curvature. The next one is member. So we have flanges in compression under cyclic loadings. They'll go back and forth, and lateral bracing is possible by the slab in one case, but when the reversal happens, you need some support at the bottom flange also. Columns have three basic actions: bending about major axis, bending about minor axis, and twisting about the longitudinal axis. We will need to worry about all of these because in general, for all these actions, what is critical is bracing, and bracing does make a big difference. In the bottom case, you have no bracing, no lateral bracing, and as the lateral bracing increases, you will increase the load carrying capacity of the member. And the higher you can take this geometric critical value, the better it is for us to guarantee that the plastic actions will be considered. Now, typically three factors control stability: geometric, material, and boundary conditions. So you notice that material is E, geometric is I and L, and boundary conditions is about the most critical item, and that is the effective length factor that we're talking about. Just to push a little harder on that, the effective length factor will be dependent on the end conditions of the member. And this is what you know from the Indian standard right now, that it can go from 0 to 1 to infinity in the case of sway structures, and 0 to 0.5 to 1 in the case of the non-sway structures. But what is also necessary for us is to understand that steel structures by themselves, if you're looking at moment frames, cannot resist the earthquake shaking, which means that you need to put some stiff systems into it. It could be a steel plate structural wall or a series of them, or even a concrete core. When you do that and sways allowed or not allowed, this is going to make a big difference. And so you need to bring about the consideration of shear deformations, especially when you use these mega columns in tall buildings. Your beta factors will really play a big difference in the case of design. So once again, when I have a member, I need to make sure that the plastic rotation that I am generating at the ends of the member, but that's where the critical sections are. That's where the moments are largest in the case of earthquake shaking. And hence you will see that as the section becomes slender, you will see that it's not able to reach the or stay on the moment capacity. If the sections become very deep, they will not reach the moment capacity. But somewhere in between, there is a ratio of aspect ratio, slenderness ratio, L by D ratio, about 10 to 14, that will give us a reasonably good sort of moment rotation curve of the structure. The next aspect is connection. There are connections that we do with the strong axis in the case of I sections and weak axis. But in the case of box sections, these are generic connections in buildings. Now, just to clarify, connections are general words. But what is important is in steel structures, we define another quantity called joint panel zone. And that is actually referring to the common area between beam and column, but it is a part of the column alone because the column goes through and the beam is joined to that column. And the fixtures that we use, it could be cover plates, rib plates, web angles, seat angles, cleat angles, all of that, or continuity plates, all of that will become the connection items here. So the catch is that when you look at a joint, you will get under lateral shaking, unsymmetric moment actions accruing in the beam. So the two beams go in one direction and the column stubs go in the other direction. Now, when you look at the joint itself, the joint region, it is going through a major reversal of bending moment, which means it's going through a serious shear force action, which means that there is going to be a diagonal compression and diagonal tension. So now you realize suddenly we are in trouble because moment compression comes into picture. We are not able to just walk away without worrying about B by T's and D by T's. Also, you notice that there is a kinking that is happening locally at the junction of beams and columns. Because of the kinking, you also notice that there is excessive demand on the welds that are there at the junctions of beams and columns. Now, if you notice the overall deflection of a building, in steel buildings, there are three contributors to the overall deflection. Of course, the column and of course the beam, but now, of course, the joint also. The joint also plays a significant role. It can be up to 30–40%. In the case of steel buildings, the joint can enhance the deflection. So depending on how you have designed, here is the case where column is the weakest, the panel zone is stronger than that, and the beam is more stronger than that. So you will get this behavior. As you make the joint panel zone weaker, and the beam is next and the column is next, you will get this. But the more desirable one is where the beam forms the plastic hinge, the joint panel zone is next, and the column is the third here. So in that sequence, you'll need to say that inelasticity in the beam is permitted, inelasticity in the joint panel zone is not permitted. So we need to develop a hierarchy, and codes have not yet clarified this adequately. We're praying that over time, this will get sorted out. Now, there's connections that are coming in. So what we saw just now was a simple planar connection, but most connections are not like that. We will get 4 members meeting, 3 members meeting, 2 members meeting at a joint at a perpendicular direction. And so these are going to cause more trouble to us because the web joint panel zone is now going to be connected by welding with another member coming in the normal direction. As a consequence, you will see that we need to now carefully design the flow of forces. And for corners, the box sections are also going to give us more challenge. Because in the case of I sections, you can put continuity plates, but in the case of box, it's not so easy to put a continuity plate. In most cases, you won't be able to put a continuity plate. So how do you really bring continuity of the two beams that are collinear? The story is very similar in the bottom of the columns sitting on foundations and exactly what is happening. One of the important points that is discussed is that the connection should permit us to rotate by a certain amount if you really want plastic moment actions. Usually they give us numbers like 0.002 radians, 0.003 radians, and 0.004 radians. If you can give 0.004 radians of rotation through inelastic action, then it is said that it is earthquake resistant section. So you look at rotation on the bottom axis, moment on the y-axis. So here is a connection that doesn't reach either the strength or the ductility or the rotation. This one doesn't reach reaches the rotation but not the strength. This one reaches strength but not rotation. Of course, the ideal one is this one, where we are able to ensure the plastic moment capacity, also ensure the not 4 radians of rotation. Now, connections, when you look at these different connections from I sections, you will notice that you will have a spectrum of them. These connections will tell you that some are weak, some are flexible, some are semi-rigid, and some are rigid. The best connection for us, when you look at strong axis I sections, your connections, the rigid connections are the ones that are recommended for earthquake resistant regions, and the others are for non-seismic regions. Like if you do weak axis connection, again, you have a spectrum of them. Sorry, you have a spectrum of them. And you will again require a fully welded connection in that case if you really want to protect that structure. And you look at the box column beam connections also, the story is not too different. Again, you're seeking a fully welded connection. Now, this is classically the philosophy that was adopted in the design of structures. Now, so far we're talking about welded. Now let's look at some bolted stories. So obviously the bolt hole is not going to remain the circular one, and it will elongate into an ellipse. Now, when you look at bolts being subjected to shear forces, you will notice that there will be a slip. For some distance, it has to slip, and then only it will engage. And that is what is our worry, that when you look at this kind of force transfers under earthquake conditions, ideally, if you didn't have a slip, you will get this as the force displacement relation. But if you have slip, you will get a very different relation. And that is what is our worry, that this pinching, because the friction is lost in high strength friction grip bolts because of the loading that is coming in the way it is coming in from the different parts of the structure. There is a clear slip that you can see in the pinched hysteresis loop. If that slip were not to happen, the orange would have become the green cycle. Now, one important point when we talk about connections is the D regions and the B regions. D regions are disturbed regions, B regions are Bernoulli regions, and we are looking at the connections in the D region. So let's spend a little attention on what happens in the D regions when you connect a beam to a column, right? Typically, we're looking at plastic hinges to form at the end of the beam. And so you will get an equilibrium shear force corresponding to plastic hinge. So here is where we are looking at MPR, the probable moment capacity that you're going to achieve. You remember you talked about uncertainty in the yield value, uncertainty in the ultimate value, and then uncertainty in the redundancy that we have. All of it together will contribute to plastic moment capacity, right? And so let's understand now you have a moment. Classically, what I've been saying, that the moments will be carried by flanges and the shear force is carried by the web. This is what we have been telling everybody, and even all the books maintain that even today as we are speaking. But the fact is that when you apply this moment and the shear force, the force transfers very differently than what you notice in this case here. Important point to capture here is the web is doing nothing when you have the shear force and moment transfer happening. The web is actually not transferring anywhere. In fact, if you connect the web, it is detrimental to the connection, and it will cause additional stresses which are not good for the beam to column connection. Which means now that this assumption that we had in the yesteryears is not valid. Which means now that we need to now allow the forces to flow through diagonal plates, the rib plates, and for making sure that near the welds here at the column face, no yielding should happen. You need to increase the amount of steel here. So you get a cover plate here, and the flange plate together will take you to push the plastic hinge away from the edge of the cover plate, right-hand side edge of the cover plate. And once again, a reminder, the beam web is not connected to the column. And so the nominal plastic moment capacity needs to be enhanced. with the actual yield stress, with the actual strain hardening that happens, and the actual compactness of the section, depending on the B by T's, D by T's, you need to define those. Another important item we saw just now is the weld. We were taking weld for granted. And if beam has to form the plastic hinge, the grade of the beam material, steel material in the grade of the beam should be lesser than that of the weld. Also, the weld and the column should be about the same. There should be some amount of matching that should happen. It's not that you'll take an unduly strong weld or unduly strong column. That's not again desirable, and they have seen unwanted conditions. So, what is the strategy in the case of connections? Classically, it has been said that the members may get damaged, but the connection should not. And this has been written poetically by a lot of our known poets of the nation. But the story has changed. The earthquake resistant connections now, in the recent times, tell you that no, the member also, we want to use that. We can't afford to change our members so many when an earthquake happens. So the member should not get so damaged. But I need to do something with the connection in which connection can get damaged. I can use it like a fuse and then replace that connection again after the earthquake, but not the member. This is a smaller material to replace than a beam, which is 8 meters long or so. So traditionally, we have been asking for a stiff and strong connection. But now there are studies which tell you that we need a stiff and a weak connection, but it has to be a ductile connection. Earlier, we were not talking about ductility of connection, but we are talking about here ductility of the connection itself. So the plates that we have here, the fuse link plates here, the red ones and the blue ones at the bottom are to undergo inelastic action. Also, when you have two stiff systems, braced frames or steel plate structural walls connected by link beams, then those link beams also will have a small segment of it called a fuse there. Again, that fuse will go into a cyclic plastic shear, and best is not to put ductility into them. Okay, so now we are talking about the classical connection on one side, rigid connection, which is in practice. And then research tells us that we need flexible connections. And that is where in 1990 story onward, 1990 onwards, we are seeing a lot of proposals, but they are all still in the research stage and have not really entered the design standards. And the last on the list is structure. And there are some lines coming in. I pray that somebody who is using the pen may avoid that or clear those lines for us, please. So the structure requires 7 virtues. And if you really want the structure to be ductile, where do we start is the question. So we know we have a good material. We know we are making this section a reasonably good. We're able to design our structures. And then what is important is in the backward direction, we need to also evaluate our performance of the structure. This is crucial for us. So you take a steel frame and then you start pushing it horizontally. You will notice that today's design standards will cause plastic hinges to accrue only in the bottom part of it, which is about 1.5 to 2 times the width of the building at the base. Only up to that the hinges will go and not beyond that because of the way the clauses are written right now. And the way they're written right now will cause all these hinges to happen simultaneously, and suddenly the structure becomes plastic, which basically means that there's a story mechanism getting generated in the bottom of the building. Now, this needs a thorough study to improve the performance of the steel frames in the country. Now, you also notice that the strain hardening is not getting utilized significantly because between the first hinge and the last hinge before collapse, the rise in the strength is only about 10-15% here. But that is something that we need to watch for. We need to see if we can, this slope of the load deformation curve can be made steeper by using the strain hardening on the stress strain curve of steel. This design strategy controls the overall mechanism. of the structure, collapse mechanism of the structure. So if you have a parking lot in the ground story without any structural walls, or if you have tall stories in a hotel building, or if you have tall stories in a commercial facility where you have cinema halls, or you have a dining place with glass windows all through on all four sides with everything exposed and no stiffness elements here, then you will notice that you'll create through functional reasons, you are creating flexibilities in the structure and you can get poor performance during earthquakes. Once again, the current design doesn't guarantee this, and that is why we need now to predetermine, but the standards are currently not guaranteeing. Only member hierarchy is getting addressed, but at a structure level, between two adjoining members, there is some control that is being recommended. But at a structure level, we have not really examined that as part of the clauses. So when you want a good mechanism, we need, especially for critical buildings, we need to go through the reverse loop also and get the best in that. One of the important points that is coming in steel structures is the level of axial load in the columns. If you have less vertical members, you will see the fluctuation, the axial load will be very large. And as a consequence, you will notice that the axial load, if it is small, you will get a much better load deformation curve than when the axial load is large. If the axial load is large, you get a brittle performance, and that is what is crucial for us, that we don't get into this kind of behavior. The red behavior is not acceptable for us. Now, those of us who understand PM interaction diagram also will tell us that we are looking at a axial load level, which is about 20% of the yield value. And if you go beyond 20%, you'll start seeing sharp drop in the curvature. And in the best case, about 30-35%, including the oscillation due to earthquake loading. And that is where we say that it is necessary for us not to overload beyond this. Our good news has ended the moment we recognize that not just P and M, but P and M come along with V. And so the three-dimensional interaction of P and V has to be recognized in our design procedure. Only then we will be able to ensure that ductile actions will happen. Otherwise, we can have even brittle failures through diagonal compression actions activated by shear. So the three structural systems that we have for steel structures are frames, trusses, and walls. Walls, these are steel plate structural walls. I'm not saying concrete walls, but steel plate structural walls. And if you evaluate them on a count of 10, you will notice that out of all the systems that we have, which is concentric braces and eccentric braces that we have, you will notice that these braces are not going to be small elements. They are not rods. They're not tie rods. They are as good as the columns and beams, if not sometimes even more sturdy than that. But and the structural plate shear walls are very convenient to use through the height of the building. And you notice that the walls are going to make a big difference in terms of performance of the structure, that the columns and beams will get less demands as you add more walls. By increasing member sizes, column sizes, we are not going to achieve much of that. Just to demonstrate that the effect of the structural system, we're taking a simple portal frame and looking at two rotation capacities. One is a very low rotation capacity, one is a large rotation capacity of a section. And then we will do the lateral load analysis and notice that more is the rotation capacity, more is the overall structure ductility. That means there's a direct relationship between the two, right? So we have many curves here. First is a portal frame, a diagonal downward brace, diagonal upward brace, a diagonal X brace, and finally a V brace here, the chevron brace. So there is a need to sort of recognize that different systems, brace systems, have different merits, and we need to accept one of them as a proposal for the design of the structure that we are getting. We will get surprises like short columns when you put elements next to these members which are not desirable, right? If you want to rate these structures, very simple. Frame structures are the poorest. Frame with truss, the braces are good, but the best is still frame plus wall. So we are looking at in brace systems, two cases, concentric and eccentric. Eccentric is a shade better than the concentric brace frame. So the strategy here is to keep it simple. Moderate grade of steel, good structural system with redundancy and stiffness, and capacity design to be adopted, and connections at fewer at site, and no slip in the connections is the statement that will. I'll stop here or try to close the discussion by saying we have ductility at 5 levels, understood. We also notice that material is very good, but we have some actions which are detrimental to overall ductility. And so we are constrained to have combined material and geometric nonlinearity in our structures. Yielding is expected, and so we need to rely on deformability of the structure. We need to enhance that, and the post-earthquake, post-yield deformation is the most crucial. Let's just summarize by saying material ductility is very good for us, right? We have steel, and we have section ductility, which is going to give us a little lesser curvature than what we have in the case of steel as a material. And in a member, we get lesser rotation capacity than what you get in a steel's section. And we have ductility in the structure, which is 3. Now, as you notice, we went from 300 to 30 to 10 to 3, as we went from material to section to member to structure. Just let's go back once more. You recognize that we have connections. Whenever you want to convert a material into a section, you need some connections. And section to a member, you need some connections. Member to a structure, you need connections. So connections are all pervasive in our game, and they're also contributing to this madness. Let's recall once more material ductility. If you look at the right-hand side picture, the entire cross-section is in uniform state of strain. And so you're able to get the full material to be active completely. And that is the best. You'll get 300 material ductility. You come to a section, only the ends are getting utilized. The inside is not getting utilized at all. And hence, your section, ductility drops from 300 to 30. This is section ductility. Here only flanges participate. Then you come to the member ductility, where only member ends are participating. And so you'll get the plastic rotation capacity to drop down again once more from 30 to 10. But then when you do the structure ductility, where all these members are getting connected with connections, and you saw how connections get into trouble, the ductility drops down from 300 to 3, right? So we need a delicate balance between strength and ductility, and very high strength and very high flexibility are not acceptable to us. Very high ductility is not achievable. Only moderate ductility is achievable. So the expectations are, when you design new structures, that material should be tough, moderately strong and ductile. The section should be plastic. Member should be flexible enough to form plastic hinges, not to undergo geometric nonlinear effects, and to maximize material nonlinear effects. The connection should be stiff and strong. As I say that, I do recognize that a lot of work is happening to now make the connections weak and ductile also. So we'll watch for that a little more. And then finally, we're looking at a structure which has got high redundancy and adequately held at its boundaries. One thing I will use to close the discussion today, we are in a hurry to use high strength steel without due R&D. And this is applicable to both bars and sections. I look at the toughness values for high strength steel. They don't meet the requirements that we have for ductile structures and in the Indian standard itself. We have weldability with carbon equivalent shooting up beyond 0.5, while you might say that this is okay for gravity load systems. For seismic applications, this will still be an issue for us. Heat affected zones are not acceptable, especially connections failing is not a method that we want to adopt. Plastic curvatures, you will notice that if you use very slender sections, if you want to economize and use slender sections, you are actually not giving us much ductility, curvature ductility, right? We know that plastic rotations become very small if we have sections that do not stay through for different conditions. So when you have normal steel, we have ductility at the material level 300, at a plate level or a section level 100, at curvature member level 30, plastic rotation of the connections, if you come into that, 10, and finally displacement ductility of the structure will bring it down to 3. So what's the story with the high strength steel? Sigma y is large, so A will be small, I will be small, K will be small. So material problems are that ductility is going to be compromised. Buckling problems will enter the game because of the very slender sections. And construction problems will arise because of the poor choppy V-notch values and poor weldability. In fact, high strength is not used effectively, and hence we are saying the rating is definitely not acceptable. So it is simple. If you want to choose high strength steel, do some more studies, be convinced what is good for us. As of now, prima facie information tells you that the ductilities are very low and may not be acceptable for ductile regions. So ductility, despite our best efforts today, the structural ductility is low. What it tells you is we started with 300 and we're finishing with 3. Now, don't worry about the neighbor's cow. Even reinforced concrete structures, the same story. You start with concrete, which is 3, and steel, which is 300, and the final value is still 3 for concrete structures also. So there's nothing to choose between concrete structures and steel structures. But what is crucial is that we recognize that this drop that we have from 300 to 3 has to go through a formal rigor, and we need to establish that for all grades of steel before we start accepting them. If you get a structural ductility of 1, you know that there's no post behavior, which means that we need to be watchful whether they are applicable for high earthquake regions. So all we would say is all that glitters is not gold. We might get something new, but we have to do decent R&D before we can accept it. In closing, I will say we need to get the big picture right. And that is essential. Before we accept anything, we need to make sure we tie up all the ends, understand where the monster is, and act accordingly. And I think the key point that I started with, I'll close with that. The number of teachers that we have in steel structures is dwindling, and something serious needs to be done. Something more formal needs to be done to bring this academia into the practicing world of steel structures. So we need a capacity development action for steel structures in India, both for professional practicing engineers as well as for teachers and teachers to begin with. I'll stop here by expressing my deepest gratitude to Mishra Saab and Ghosh Saab for bringing me here and giving me an opportunity to share some pictures and some images and impressions of what we have been watching over the last 30 years. Ladies and gentlemen, thank you for your time and attention.
Thank you, sir. This is MM Ghosh from INSDAC. So we might be having question answer sessions. And to start with, let me start the question answer with my question first.
Ji.
Sir, we have found many new things coming into the picture, which we were not aware. So I hope this will be converted into the codes. So what do you look forward? Because in IS 800, there is chapter 12, which is dealing with earthquake. Then it is IS 1893. So there might be some other codes also on detailing. So can we have a single code, or shall we in bits and pieces as it is now?
Yeah.
That is point number 1, sir. So the second point.
Can I finish one by one? I may forget.
Okay, sir. Okay, please.
Sure. So on this thought, the good news is that chapter 12 will be withdrawn from IS 800. There is already a new standard IS 18168, which is for design and detailing of steel structures, steel buildings, which are meant for earthquake safety. So the IS 13920 that you know of for concrete structures, a parallel to that is IS 18168. And we also agreed upon that the the Steel Committee of BIS and the Earthquake Committee of BIS will have a joint working group for all future revisions that we will undertake. Okay. So which
Okay.
means that you don't have two horses to ride on. There'll be a single horse and that horse is ready. In fact, IS 13920 part 1 and 2 are on wide circulation. And part 2 will tell you that for buildings, the story that I have discussed, almost 80% of it is there. Except that fuse link connection that I told you, it is on the research stage. Except for that, we have brought in most of the points into picture. But what remains to be controlled is the temptation to make the structure cheaper by using thinner and thinner sections. First. The second point is the temptation to use higher grades indiscriminately without understanding the implications. For example, the higher grades may not be as simple as adding an epsilon factor in the standard in the expression for estimating B by T's and D by T's. We need to do tests before we put in that epsilon. Right now it is there already, and depending on the grade, it will do a penalty on you. But the fact is that we need to establish it because other people's lives are at stake. Who knows? It may be my life at stake when I enter a building that has been, designed with this clause, which is not necessarily experimentally verified in full-scale testing in the country. So my urge for our community will be that we need to have a more formal approach to approving newer materials coming into picture, newer technologies coming into picture. One of the worries that I have is that we are building structures without standards for it, and pre-engineered is one example of that, right? And you can't make pre-engineered structures in high seismic regions which do not necessarily meet the requirements of the Indian standards. Now, if you permit me, I can even say that we should wait for some more time before we are able to create a standard for pre-engineered. We should not use international documents just like that because they may not be applicable for all regions of India. So whenever you bring a new technology, you bring it in a small way and not openly for the whole country. India is one country which has got extreme differences, a factor of 5 difference between the lowest seismic zone and the highest seismic zone in terms of acceleration factor. And so my worry would be not to have a single paintbrush for everything. We need to have the smaller, thinner brushes for artistic work and then a flat brush for walls, right? So I will hold not using this as a municipal corporation, as a government body, let us say Indian Railways or any other organization which is using these structures, FCI or whoever, that they need to be watchful and not approve it unilaterally for all areas in the country because there is no standard for it. So sort of regulated technologies is not a practice that I would support. I would think that we need to be very careful because it's other people's money, other people's lives, and other people's property. We can take your second question.
So the second question is, we are comfortable with the CBF, the concentrated brace field. Now you have shown pictures of EBF.
Yes.
So is it being included in the code or
it is included already in the new standard, which you have IS 18168. We will drop IS 18168 the day 13920 in its new avatar is accepted. That will get withdrawn. IS 18168 will get withdrawn. And 13920 will prevail, right?
Okay.
And it's already included in that. Eccentric brace frames are
Okay.
allowed already.
Right, sir.
Ji.
Okay, sir. I would request the participants to ask questions. There are certain questions in the chat box. Sir, if you can go into the chat box and reply to it, that will be quite fine.
Okay. Chat box. I have a chat in which I'll go down.
So you open the chat.
Yeah, I opened the chat.
Yeah.
Okay.
Could you find any questions?
Yeah. If we require, this is Prashant Lele Saab is asking, if we require a low yield stress for good ductility, why are the manufacturers permitted to sell high yield stress in the market? How do we control this? For example, Fe415 is not available in the market. How do we deal with this? How is this dealt in the other countries? If I tell you the story of Taiwan, Taiwan is a small country, but it is a very earthquake-prone country. And what they have done extensive work for 10 years or more, about 12 years, 14 years. And then they've recently concluded that high strength is not good for them. Okay, this is high seismic region. Taiwan is an island that got created out of earthquakes. And they have had the worst earthquake in 1999, the Chichi earthquake. And they have followed it up with deep studies, and they've just concluded in the last 25 years, even though some studies were slower to begin with, but the major focus on high strength came in the last 12 to 14 years. And they concluded recently that it's not the good thing for them. Now, wisdom says that we need to examine it for our country also. And one way to be convinced of what they have done is to do some of those tests here. Now, many of us will argue that why should we redo the tests? Because the professional practice is different there and here. The way we do welding there is different from the way we do welding here. The way we have sections there is different from the way we have sections here, and so on. I can narrate the whole story. So the bottom line is that the R&D has to be stepped up, in which I would say the Ministry of Steels and Mines will come in a big way into formally trying to do some study and show it to the people of India. Threadbare. Let's go on a white paper and show what is good for us, what's not good for us. But this will require full-scale testing. We need to step up on test facilities in the country. And so it is time to do proper large-scale testing of structures, not just scaled-down models will give different behavior, especially non-linearity, they'll give different behavior. Okay. So I would say in open market economies, they're allowing everything. But that's not the way we run in our country. We are a little more conscious and careful. We have to be careful. Now, what's the next question is, what is the effect of floor bracings when seen from ductility point of view? See, the floor bracing will brace the floor. And if you have a plan aspect ratio less than 3, that's good. And we are very happy with that. But that doesn't talk about the main members, which is beams and columns. So floor bracing allows the whole building to act like a box back and forth. But as far as ductility is concerned, we're talking of those members which go into plastic actions. One of them is beam. And in some cases, if you, as I showed you, the columns also will form plastic hinges. So we need to worry about the hinges happening in the columns also. So floor bracings have their merit, but don't address ductility of the whole structure at all. Another one says, is deformation and ductility permanent? If so, will the structure have permanent deformation since ductility is beyond yielding? Normally, if you have a shaking, that is far field shaking.
ಎಲ್ಲರೂ ಹಾಗಿರೋದಿಲ್ಲ ಸುನಂದ, ಎಲ್ಲರೂ ಟೆಕ್ನಿಕಲಿ ಚಲೋ ಇರ್ತಾರೆ. ಕಲ್ಚರಲ್ ಮೈಂಡ್ ಸೆಟ್ ಮತ್ತು ಪಾರ್ಶಿಯಾಲಿಟಿ.
Naresh Shankar, can we mute Naresh Shankar? Okay, he's been muted. Thank you. So what we're looking for, and Naresh Shankar has gone into display mode. Okay. So we're looking at ductility. Is it causing permanent displacement? Answer is yes. If you have far field shaking where the pulses are not present, the near field, there are near fault pulses, high velocity pulses. When high velocity pulses come, you'll definitely see large plastic residual displacements. But in the far field conditions, this is not happening. So that is the reason why I said moment frames will not help survive people. If you are in the near fault regions, you need to have very stiff system. And that is where steel plate structural walls or even concrete structural walls are mandatory to save people. And so permanent deformation can be countered only through a stiffer system where the displacement demand is significantly reduced by that. But having said that, let me confess that near fault effects are approximately handled in some country standards, but a formal work is required in India for us to do a codification of the effects of fault slips in the Himalayan region or in Andaman Nicobar, Northeast, and in the Gujarat region. Not to talk about surprise earthquakes in the Indian Peninsula. Somebody says, but nowadays we are using high strength steel. and 415 isn't used more. I share your agony, I share your pain, and let us have tea together. That's all I can say. Because our appeals to the manufacturers and some higher ups is to do a joint study with the cement steel manufacturers working together to answer this big question of why market would discontinue an important low strength steel. For example, I'll give you for transverse reinforcement, the calculation still will be done by 415. Even if you use 2000 grade steel, we will still use 415 because transverse reinforcement is confining reinforcement, should have a minimum diameter, minimum area, so that we are able to give stiffness to the concrete in between. Likewise, if you raise the higher strength steel sections and higher strength in steel sections, you will reduce the thicknesses of the plates. And as I said, you will not use high strength anymore, because once you go into geometric buckling, you will not use the strength of the material. Okay, then design codes for lateral resting system. There's a question. See, everything cannot be codified. What the code is trying to do right now is don't do bad things, is what the code is saying. On the list of good things, if you write, there'll be very few. Then you'll say you suffocated us. So what the world's practices in codes is that you take the various earthquakes, see what have collapsed, and say, don't do those. For example, flat slabs, don't do those. For example, moment frames, don't do those in high seismic regions. This is how the codes have been written, and that is how we will allow the engineers to apply their mind a bit. Right? Now, somebody is asking question, which foreign country codes are acceptable for use in India? Answer is none. Right? You need to write your codes, because if I tell you anything is yes, you will take the capacity code from India and the hazard code, demand code from there. This is not acceptable. You have to take both demand and capacity code from the same country. I know of some organizations which use the other country codes, both demand and capacity, and build structures in India. But still they have the responsibility of showing that they are within the Indian standards. Whatever the Indian standards are right now, they should comply with the Indian standards. For industrial structures, most of the clauses of 18168 are too difficult to implement. Well, you cannot compare unsafe and safe practices. One. Second, industrial structures tend to have larger sections, and so the amount of welding that you will do or connections that you will do will be very large. And that is where now thinking has to start as to what will be the strategy for industrial structures in India. We can't continue by the old method of buildings and industrial structures, same design. We can't continue by that. We need to change that model. And that is the motivation for us in our earthquake committee, where we said, for industrial structures, we have a separate standard for hazard estimate, IS 1893 Part 5, and we will create IS 13920 Part 5. This is where I request all the colleagues from the industry to come in happily and join the working group and suggest to them what are the good things that you think you want to include in IS 13920 Part 5, which is for design and detailing of industrial structures. Okay. Good. This one, what is the next one?
What is the impact of the grade of?
What is the impact of grade
bolts
of connection bolts on connection? Also, yield strength of steel plates available market, which are recommended for buildings for PEB structures. Okay, I will not talk about PEB. As far as the bolts are concerned, there's already a specification for that. If you look at IS 18168, it's there. And the yield strength of plates, as we told you, you will follow the IS 18168 for now, because that's the law of the land. But as we do more research, we may even alter those numbers. For now, they are adopted from another country's standards, but we are praying that we should be able to do in-house R&D in the road ahead. Performance of composite structures, will they perform better during earthquakes? I shouldn't throw the wild guess here, but you have a hybrid structure, and so you need to do some testing. For basic mono material itself, we have not tested, and I would think that it will take a little longer for us to do composite structures, unless a government body sort of takes it upon itself, the gauntlet, and says, let's do for all the systems, classical monomaterial as well as for hybrid systems. IS code is silent on ratio of thickness of flange to thickness of web. Thickness of flange to thickness of web. What is your opinion in the same? Well, you're comparing oranges and apples. You stay on the flange alone, and B by T, D by T are different issues. So stay on individual. Don't compare thicknesses across here. You need to protect each of them independently, because remember, the boundary conditions of the two plates are different. Can we use high strength steel for gravity load and use low strength steel for horizontal load in the same structure? My question is, are you able to guarantee that this part is the gravity part and this part is the horizontal part? Well, I'm saying that because we have in the standard written that you can choose these structural systems which can carry lateral load, which means about 90% of that, and only 10% should go through the remaining. One of the things that is yet to be examined seriously is, when I use two grades, differential grades, will galvanic corrosion be hastened? Is where the worry is for us. And so if I recommend anything without discussing with the metallurgy colleagues, it will be improper. So I'm praying that our metallurgists will have to come in a big way to answer this very important question. This is also right now plaguing us in the reinforced concrete section also, where we are using one grade is transverse, one grade is longitudinal, one is for column, one is for beam, and so on. That mix and match is happening, but IS 456 will resolve that matter soon for you. Somebody is unhappy, he says, but could you resolve, could you help us how to deal with this, as is mentioned earlier? Well, I am one citizen of India. There are 140 crores minus one more people in India. If you take away all the babies, maybe 110 crores. And if you take away all the non-technical people, maybe you will get about 1 lakh people. So we will need to discuss with 1 lakh more people and get some advice on how to deal with this. But right now, there are some wise people in the higher offices. I'm praying that they will soon agree to come on table and then start doing some formal R&D to save the people of India. We understood that elongation is not a measure of material ductility, but more of its flexibility and bendability. Our codes provide as a material property, as their measurable product related ductility are not to be compiled with by the designer. Okay, let me clarify. You're saying that elongation is not a measure of material ductility. Elongation is a measure of material ductility. Okay. Flexibility of the material is not flexible. When you make the material into an element, that is when the flexibility comes into picture and bendability comes into picture. So steel as a material doesn't have the flexibility, but steel as a bar, steel as a plate has flexibility and bendability. Because when I say flexibility, I'm talking of reverse or inverse of stiffness, which means I need a length, I need a boundary condition, I need the material property E, and I need the cross-sectional area. So the bendability depends on diameter or size, thickness of the plate, and so on. Are there any measurable properties related to ductility to be compiled with by designer? So let me be very clear. Your strain ductility is already there in IS 2062. It's asking minimum certain percentage of steel of elongation. That is good enough. But what I was saying was that this strain ductility, if you have to convert that into the structure ductility, you have to go through so many other stations, and at each of those stations, if many passengers get down, your train will go empty or only with 3 people to the final destination. That is what I was saying. Okay. Then somebody is saying for beam column moment connection and seismic frames, whether we have to use demand critical weld as stated in 341, eventually you'll get to that. But as of now, I request you to read IS 18168. It should help you. You look alike, Mr. Dr. Virendra Hegde from Karnataka. Thank you. Maybe I was told 7 people look alike in this world. You have met 2 who look alike. So hunt for the remaining 5 and we'll be all having tea together. What, in your opinion, on the temperature analysis of steel structure. So in the new avatar of NBC, we are separating the temperature analysis into two parts. One is ambient temperature analysis, which is where the modulus of elasticity and the Poisson's ratio of steel will remain the same. So you can do normal structure analysis, only talk about elongation, compression, contractions. The second analysis is fire-related analysis. The chemical composition gets modified, and so the modulus drops down. That's what I said. When your endurance, after 300 degrees centigrade, the steel starts losing its strength. So for that, you need a very different analysis, and that is what the Fire Code of India will tell us. And that studies are underway. Whatever is the current fire code, a significant revision should happen soon in the road ahead. But this will be elaborated to some extent in the new IS 456, that's the new NBC that is coming, and you will hear it in that. Nowadays, it's a common practice to do PEB, to design structures using Indian wind codes along with American codes. So I want to go to a restaurant and I want to order one vegetable sabji and not mixed veg or mixed jal firezi. In high seismic zone 4 or 5, can we deal with industrial structures with high crane capacity of 500 tons? Outer leg, roof rafters need to be designed as per section 12. Yeah, we're discussing projects here. So maybe what you could do is travel to the nearest institute and chat up with the colleagues who are good at that, and you will be able to do the projects. If we comply with the code, so there's a project-based question. Let's avoid project-based questions.
Good afternoon, sir.
Also, yeah, please wait. Let me finish these questions so that people don't get shortchanged on this. In high seismic zone, heavy crane structures, there is a large distance using HSFG. Welding is still practiced. Okay, so that's a choice. That's why we are saying that it is a matter of the designer and the proof consultant or the peer reviewer to decide what is appropriate for a certain situation. I'm talking about a cold climate region. I'm doing, let's say, riveting there, or even I need to be a little careful when I do rivets. But if you can fabricate that girder in a factory, not in cold countries, a cold area, but take it from the plains up, maybe that's a different answer. So each project will require a different way of addressing the matter of bolts versus welding. And what I understand is that there is a gradual shift that is happening towards welding in seismic areas, because HSFG, if it is not done correctly, if you don't have a torque wrench that is well calibrated and regularly examined, then you will have trouble in the road ahead. And that is where the concern is. When you don't have QA, QC at site, you will be worried about that. Then there is a question, two questions. Which Indian standard provides clause for ductile detailing of welds? No. Welds are not ductile. Steel structures will be ductile, and welds will be appropriately chosen to make the structure ductile. Is behavior of the single brace frame shown more ductile in compression rather than in tension? Okay. So maybe he's going to a specific slide here, slide 134. And what we are looking for is that when the brace is in tension, we are supposed to see better behavior than when the brace is in compression. If there is a slip of switching the figures, my apologies, but you are standing very closely to the reality in your observation. Okay. So we have finished the questions on the chat box. So if there are some two new questions, no. When is new NBC expected? Would you suggest using draft codes for design until it is released? NBC 2025 is the date. And so we are right around the corner, but a lot of hard work is required. And should you use draft codes? When it is in wide circulation, and if you think that's good practice, you should use them. And if it definitely removes an error or a deficiency in the existing standard, definitely use them. For steel buildings, low-grade steel meaning 345 or higher than 345. Normally, we're saying, I'm talking about yield strength. We're talking about 250, 345 is like reasonably good for us. Thank you. Thank you. Then TF by TW. Can we keep adding flange plates to a section and enhance the properties? Yes, that is one way that people would do, but there are cautions to be adopted when you keep composing a large number of flange plates to be added together. There are some conditions to be adopted there. When do we get 1893 part 1 and 2? It is in the galley proof stage. So anytime in the next month, maybe. That is what we are praying for. Yeah. September should be a time when we can expect it. We are at the galley proof stage right now.
So that ends the questions in the chat box.
In the chat box, we can take direct questions if there is time.
Yes, sir. I find Professor Mahesh Tandon there also. I would
Okay.
request if he has certain questions, because he is quite favorite to us. We have interactions. So
Yeah.
over to Professor Mahesh Tandon.
Tansab, please come. I request others to raise your electronic hand and not your physical hand, because we can't see your physical hand. Electronic hand, Tansab ko nahi chahiye, but Tansab, you can please raise your question.
No, it was wonderful to listen to this very enlightening piece of technical exposition of what should be done in steel structures.
Ji.
I have only one question, that this is a little confusing for the practicing engineers.
Ji.
For one thing, to even understand properly whatever has been said in the last 1.5 hours, we need to perhaps listen to your lecture at least a couple of times more. So is this going to be available on YouTube or something so that one can keep listening to it?
Sir, I understand it is live on YouTube, so I'm praying that it will stay on YouTube. That is one. But what I'm worried more is that if you are not able to understand, you have to hear it again and again. That means I need to improve, and next time I'll try and do better.
No. I think that it's, there are too many ideas which
Yeah.
are new,
Yeah.
and to absorb them takes time.
Yes, it does. One needs
So-
to do numbers oneself at some point of time to be convinced. One need to do some experiments by oneself to be able to see the realities of some of these combinations. G.
So everybody's, experience is limited.
Yes.
So when you hear something
Hmm.
and then you try to compare with whatever your own experiences,
Yes.
if there is a conflict, then you require to listen to it again before you
True.
come to the conclusion that you are right. I mean, so what I'm trying to say is that one needs to listen to this lecture
G.
at least 2 or 3 times.
G.
It need not be one after the other, but
The ultimate criteria is only 3 for structure. So you need to hear 3 times you're saying. From 300 to 3, yes.
That is one issue which I want to say, because there are far too many new things. Maybe you should have given this in doses, like.
No, we can do it in a de-aggregated way also. But what is important is that I must confess that what I have spoken today is not new in terms of the principles, but it is new because it hasn't been brought to the Indian conditions, and we are borrowing and looking at other standards rather mathematically or quantitatively without looking at the physics behind it. That is the issue.
Yeah, but the fact still remains that there is certain things in the IS 800 or IRC
Yeah.
24 and 22.
Hmm.
This one seems to be deviating quite a lot from it.
Yes. So that's what I said. The classical knowledge has been codified, and we have not drifted from those principles for decades. So it is time to re-examine some of them. And the good news I said was that at least IS 800 and the CED 7 and CD 39, the steel group and the earthquake group will work together. We agreed the same with the steel and concrete also. I mean, concrete and earthquake, and agreed the same with masonry and earthquake. So we are going to harmonize the earthquake requirements of all the standards in the road ahead. And that is the prayer. And I hope that, the coming together will help us understand their requirements and them understanding our worries about safety of the people of India.
No, wonderful. And I liked very much your comments about the PEB
G.
because one has been having fights with them for the last 15 years
G.
without success. Because
Yeah.
now what they have done is that they say that there are two types of quotations.
Hmm.
You want as per IS 800 or
Hmm.
you want whatever they are doing, that American standard as per that.
It's not an American standard. It is a standard by a body in America, professional society in America.
Yes.
So I want to clarify that to the people of India that it's not a standard of a nation. Every professional society is free to publish its documents, but for it to become a law, it needs to pass through a little rigor. And in India, the rigor is through the Bureau of Indian Standards or the IRC or the IRS.
No, why I'm talking about this PEB is that there is such a large difference
Yes.
between the quantities that you get for a shed,
Yes.
let us say,
Yes.
being done by whatever codes they are using and whatever IS 800 results in. So
Yes.
this is not acceptable. If you are doing some work in India, you're most welcome. But you have to follow the Indian standard codes.
That's right. That's
Not say that we can give you two types of
right.
quotations.
Gee,
You want
that is true. That is true.
IS 800 or you want this American, whatever it is.
MBME.
So that is, I like that comment very much. And I think that with your help, we should be able to drill this in both the people who are manufacturing PEBs as well as those who are buying PEBs.
Right, right.
Both need to be educated.
Informed, yeah. Both need to be better informed about it. The seriousness of the matter is very high. And so I would urge both the groups to really come to the table and then do a honest, fair discussion. And I'm sure at the end of the road, both will win. Both will win. We'll find ways out for everybody.
Okay, sir.
Thank you, Nanan Saab.
Good afternoon, sir. Good afternoon.
Is this Mr. Rahul?
Good afternoon, sir. Sudip.
Sudip, kaise ho dada? After a long time?
After a long time.
After a long time?
Yes, I attended the whole lecture. It took me back to 25 years, steel structure and a lecture from you. So, I mean, I do not have any question, but it's wonderful to listen all those things from you again. And
these are those attempts that you did only, na? I'm not saying anything extra. You and your friends, they taught me and ran away. And then so I'm left with the responsibility of sharing with others. Thank you for being a wonderful human being, wonderful friend in my younger days. Yes. Thank you, Dada.
This opportunity. I just have one practice that I found in an industrial environment. There is a tendency of doing the base plate connection as a hinged one. I always oppose that from that redundancy aspect. That make it fully moment resisting base plate kind of thing. But industry has a tendency to make it as a hinge because they find it is easy to even do the manual calculation and bolt design. It is also easy to do the bolt design, only shear and tension kind of thing. So this is a tendency, and don't you think that from redundancy aspect, this tendency should be carved down?
Yeah. Thank you, Dada. One of the important points about this base plate connection is that physically you can't create a hinge, either in steel structures or in concrete structures. You will always have to formally engage the column with the foundation base plate. Now, in that situation, what we have noticed, you would recall what Rupen has done as part of his studies was when you take a column and then you push it back and forth at the base plate, depending on the level of axial load, you may not be able to reach MP at all. Right? One. Second, depending on the design of the base plate and number of bolts used, you will get a certain elastic rotation, which means it's time to put a little spring there and do the analysis and understand how much is elastic and how much is the plastic rotation. So the moment rotation curves at the base of such a at the base of columns has to be formally provided depending on the design, and that has to be used in structure analysis. You can't assume hinged. Now there is a practice of assuming hinges as and when required. Whenever there are difficulties, you put a hinge and you run away from the numbers, and then but design is done the classical way.
Yes.
That is not acceptable. You need to match both of them. The analysis should match design and design should match analysis.
Yes.
G. So we'll see you soon, Sudeep. We'll catch up. Yeah, wonderful. Good to see you. Good to see you. And the wide smile is always encouraging. G.
So do anybody have any other question?
Rahul R is raising a hand, sir. Rahul R.
Right, sir. So over to Rahul R.
Yeah.
Sir, your voice is not clear.
Rahul, we can't hear you. Sinha Saab from EIL is here. He is saying that we at EIL have started designing the so-called PEB ourselves. Thank you for sort of bring that to our notice. Anytime we have PEB questions, we'll send it to EIL so that you will be able to answer it. But yes, we will want to hear from you your experiences of what is PEB and how Tanan Saab's issue that the current PEB in the market is radically different from IS 800 compliant structures.
Correct, sir. You are very correct. We have also faced this problem numerous times because owners will be saying that that is cheaper, PEB concept is cheaper, but they don't understand the codes which they follow. And when it comes to our review and we say you have to follow IS 800, then they just vanish.
Sir, at this point of time, I'll make only 2 points here. One is that all civil engineering structures which are standing are not necessarily safe. The reason is design load has not come, and so we don't know what is the status of that. Second is, if on the matter of the practice, open ground storage structures have shown us that the assumption and design and construction are radically different, and so we get losses of life. I'll be a little worried to use anything without due rigor of analysis, design, and experiments, especially PEB. But it's important to come to table, sir.
Right, sir. Very truly, sir.
Yeah. Thank you so much, Sinha sir. We'll see you again soon. Yeah.
Thank you, sir. Thank you.
Hello.
Sir, there is a question in the chat box.
Yes.
So if you can go through it.
With latest revisions, if we design as per IS code or AISC, both will give almost same weights. Difference is in people's understanding and not in codes. Yeah, no, this is not a surprise for me because the Indian code currently, the steel code, the new one, IS 18168, is largely motivated by AISC, SPSSB. So I won't expect a difference. Okay, because the permissible stress method there is not too far away. Allowable stress method, allowable stress design is not too far away from our permissible working stress method. So it won't be a surprise at all for me. I do agree that people need to understand the design codes a lot more, and we are trying to do some writing of commentaries, and that is where we will need some help from the practicing world by reviewing those little documents and giving us better and better versions to be adopted in future. G.
So I think there are no more questions. I would request the participants, if they have any question, please interact with.
G.
Yes, sir.
Sir, I had one question.
Okay,
Yes,
sir.
Like while designing, now I have worked in Indian ACI and Euro codes also. The load factors are quite different, little bit different.
Yeah.
But when it comes to seismic load, Indian code says a factor 2.5 while designing connections. So why that kind of high value is given? Any background of that? Just wanted to learn.
So when you design a structure, I don't know if I have. Let me go back to my presentation and show you one slide of this presentation, today's presentation. Well, let me stay on this itself. I hope you understand this curve. So what happens is that, okay, let me put it in this mode. I will say the structure would have been designed for this level of load. Okay, the red point is where it is designed. So let's say it's about 300 or so. And what has happened is that the structure, when it is going to the extreme displacement loading, will follow the actual capacity of the structure. And that value is coming to about 950 or so. So 375, 950 by 375, approximately a little less than 3 is what I am talking about as the ratio 2.5 that we are giving in the structures. So this depends on structural system. This depends on the method of design. This depends on the way we do connections. So this 2.5 factor is an average factor. It varies from around 1.8 to 3.3 or so. So we took a median value for want of adequate research in the country. This requires people to do a little bit of nonlinear analysis, and that is where we are running short. And I'm hoping that in the road ahead, we'll do more of that and refine these numbers for different structural systems as of now. So what is happening? You have designed for this red dot, and the actual structure, the earthquake, is applying the horizontal axis and taking you to the yellow dots. When it reaches the last yellow dot, the force in the connection is corresponding to the last yellow dot, and the horizontal shear is so much, you can understand that will be the amount of force transferred through the connections. And that is why you need to design the connections for higher force and not for a value corresponding to the red dot.
Thank you, sir.
Naresh,
Thank
can I
you for
answer your
clarification.
question?
Yeah, it is absolutely clear for me. It's applicable for only for seismic load, but it doesn't come for
applicable
any other.
for earthquake conditions. Yes, it is applicable.
Yes.
For
Thank you so much, sir, for answering. Thank you.
Sir, I would, it's already 6, so there are no more questions also. So I would like to thank all the participants to be a part of our Foundation Day program, and obviously like to thank Professor C.V.R. Murty for his insights. I would request the participants that this presentation will be available in our YouTube channel as soon as this program ends. So as Professor Tandon was asking, you can view this one later on also and can brush up your ideas. So with this, I would thank each and every participant, and obviously Professor C.V.R. Murty for sparing his time for this event, for this program. Thank you all. Stay with us, stay with INSDAC, watch our websites. It is updated in the regular way, and you can get the updates from our site. Thank you all.
Thank you, Ghosh.
Thank you very much.
Thank you, Ghosh.
Thank you. Thank you.
Thank you, Professor Murty.
Ji.
My personal gratitude to you. Thank you.
No.
Thank you, Tandon sir.
Thank you for the opportunity. Thank you. Yeah.
Thank you.
Thank you, INSDAC.
Thank you. Namaste, Tandon sahab. We'll see you again.
Yes.
Thank you.
Thank you.
Thank you.
Thank you, sir.